I'm president of Miami Valley Audubon. This is our monthly public meeting. Looks like we've got a large crowd in attendance tonight. So without further ado, I'm going to turn it over to Randy Morgan, who is going to introduce our speaker. Randy, you're on.
Thank you, Larry. Yeah, I'm Randy Morgan. I'm one of the board members, and it is my honor tonight to welcome everybody to this Zoom presentation hosted by Audubon Miami Valley. And it's a privilege to introduce our speaker, Dr. Joshua Miller, who received his Ph.D. in Evolutionary Biology from the University of Chicago and is currently based as an assistant professor in the Geology Department at the University of Cincinnati. One thing is obviously true: Dr. Miller likes bones, and not just any bones. He likes old bones, and not just any old bones. He likes bones that have accumulated generation after generation in ecological landscapes and have stories to tell. So he's particularly interested in the historical context that these bones can tell us about species and their interactions with other species and their changes in their populations over time. And he's applied this extensively to Arctic caribou. So tonight, the title of his talk is Antlers of the Arctic National Wildlife Refuge. Old bones provide new insights into caribou ecology and management. And I'm really looking forward to hearing what Dr. Miller has to tell us about these bones. Thank you. It's all yours, Dr. Miller.
Thank you, Randy. Appreciate the introduction. It's a pleasure to be with you all. Let's see, I think I can share this now. Yeah, it's fun to talk to a group about not the study organism they're interested in. That's always a pleasure. So thanks for broadening your interest to something beyond birds, as I'm sure you do quite often. But so today, exactly right, as Randy said, my expertise is, I'm sort of a hybrid between a vertebrate paleontologist and a modern ecologist, and that I'm really interested in the historical, evaluating historical context for understanding modern ecosystems. And I brought you all here with the title of the Arctic Refuge, and I'm going to talk about a variety of things, but I hope you'll understand the journey as we go. The first thing I just wanted to highlight, this presentation does involve some unpublished data, and so I appreciate that you keep this information between us for now. So thank you very much for keeping social media out of this presentation. So as Randy said, I better get rid of this maybe, feel like, okay. So historical context is really what I'm interested in. And the point of this is, it's really important to know where a population or ecosystem has been to understand what's happening today. So for example, if you're really interested in modern bison, and there's an example of a lone bison hanging out on the landscape today, it's probably useful to consider that modern populations are really quite different and have been substantially perturbed relative to their even recent historical populations of the 1800s. So lots and lots of shifts have happened. We know of some really glorious ones, such as bison, but many of them have happened without our notice, and that's really where I'm interested in. And I come at this from the context of understanding what's happening today. That's really some of my driving interests. So I'm interested in what's called the Anthropocene, which is a time period I'm sure you've heard of and are maybe potentially very familiar with, this idea that we're living in a time when people really have an outsized impact on ecosystems and geochemical cycling and all sorts of things, including the climate. And one way to illustrate that I like is this image from the World Bank. And what you see here is the travel times over land to and from major cities across the planet. And I find this to be really a striking illustration of what's kind of going on in the sense that you can see that it really takes a day or two or maybe three to get from one place on the planet to another place on the planet. And there's very few places globally that are really hidden from even overland transportation, which is pretty phenomenal. Right? So of course, that's one way of thinking about things. We know that climate change, invasive species, all these things are leading to population changes, altered community structures, changes in who's living where, shifts in how species use habitats and that sort of thing. And the challenge we face universally is that long-term multi-generational studies are rare. And really, and I show this sort of, this is a graduate student taking some measurements, looking for some collared animals. And, you know, generally speaking, ecological studies really are kind of often stitched together programs, projects of many master students or maybe a few PhD students. So we're talking about, you know, 2 to 3 to maybe 10, maybe 20-year snippets of understanding how ecosystems function. And the challenge is even those few studies or systems where we really have paid attention for many, many decades, even those have largely been, those studies have initiated post-disturbance, following the disturbance of some sort, some ecological perturbation. So based on this, you know, with this as a setup, how do we acquire data on historical community and population states? How do we sort of evaluate what's going on today? Where do we set up preserves that capture critical habitats? And how do we create historically informed conservation and management goals, given that we have this broad lack of historical understanding? So one way to highlight some of these challenges, the first place I'm going to take you to is the Colorado River. And the Colorado is, of course, you know, one of our great natural systems in North America. Historically, we're talking about, you know, 16 million acre feet of water flowing from the Colorado River into the Gulf of California down here near Baja. And with that tremendous amount of water came a huge amount of sediment, 80 to 90 million tons of sediment annually. And when you think of sediment, you can think of nutrients. So there's a tremendous amount of water and nutrients flowing through the Colorado and being dumped down in the Gulf of California. And unsurprisingly, this sort of gift to the Gulf of California fostered an amazing diversity of marine and near marine systems, including the smallest marine mammal on the planet called the vaquita, this tiny little dolphin. Huge populations of fish, right, including amazing sport fisheries. Crustaceans is a huge stopover site for migrating birds. Incredible diversity down there, right? But one of the things you need to think about when you think about the Colorado is dams, and that should be sort of a key word that pops right into your head as you think about the Colorado. And I don't have a chance to really poll you very efficiently, but I want you to think about how many dams do you think are out there in the Colorado? And I'm sure you can start to name a couple, maybe 1, maybe 3, but how many are there? And it turns out, right, there are dams all over the place. There's 44 dams on the Colorado, all across the Colorado. 8 reservoirs of which, 8 dams worth, have over a million, hold over a million acre feet of water. So they're capturing and they're holding half of the annual flow of the Colorado every year, right? Well, unsurprisingly, when you dam up a system this severely, you basically restrict, and eventually after 1960, you completely end the water that flows into the Gulf of California. So after 1960, not a drop of water from the Colorado actually reached the Gulf of California. So what does that do? And the challenge is there was no one watching, right, at that point. That's, you know, 1960 is really, really early for ecological studies, and especially ecological studies outside of places like the US and Canada and places in Europe. So what do? How do we reclaim this information? So if you go down to this region where the Colorado River used to flow into the Gulf of California, and you start walking the beaches, you see all sorts of really cool stuff. Here's a whale skull. Here's a pelican skull. Here's a pufferfish. Here's a tremendous amount of tequila. Here is some more fish bones. Pelican bones, right? So lots and lots of stuff is sort of lining the beaches. But what do you see behind these bones? And if you look really close, what this picture is about is shells, right? And in fact, this whole region is loaded with shells. Right? And it's basically an ocean of shells. And this is a really interesting opportunity because this shell bed essentially provides a lot of the history of what these ecosystems used to be like. So if you start to really walk around and think about this system, there's no historical surveys about what clams used to be like prior to 1960. But if you go out there today, there's about 3 clams per square meter, right? So if you start actually digging around in the water, in the ocean, you get about 3 clams every square meter. Well, if you really study these mountains of clams, there's an estimate of about 4 trillion shells, about 2 trillion individuals that accumulated from 1950 to 950 AD. So over 1,000 years, it's about 2 trillion individuals. And if you start to run the math, that's really possible, only possible if you have about 50 clams per square meter. If you take into account the age distribution of those shells and how long clams last and those sorts of things. So that accumulation represents, if you compare that to what you actually find today in terms of the shells out there in the ocean, today's systems represent 94% fewer clams following the loss of water flowing into the Gulf of California, following the damming of the Colorado, right? So this is a massive reduction in productivity. And really clams, in a sense, are the base of the vertebrate food chain for these kinds, especially things like fish and birds, and even things like marine mammals like the predatory vaquita, and of course those large predatory fish. So you lose 94% of the clams, and that has massive repercussions, right? And this is the kind of effect that you can miss if you don't have historical input, right? You don't have a historical reference. So using the dead to evaluate the living, that's really what I'm interested in. And the point or the value of dead records is that the dead, in this case shells or bones, record information from way beyond timescales than we usually have with ecological surveys. And overall, there's been a lot of work to explore how these records work in marine systems with shelly bivalves and snails and those sorts of things. But the ecological value of bone accumulations is far less well understood, and that's where really I come into play. And so the real question that I'm interested in is it possible to go into the field today and collect historical populations, to collect historical data on current populations? And if that's going to work, right, you need data that are diagnostic to species, that last a long time, that provide that multi-generational record, and that are representative of the populations and communities from which they're drawn, right? And we all know that everything out there, mammals, which is what I've sort of keyed up on, we all start like this, right? Cute and cuddly and wandering across the landscape. And eventually we end up like this, and these bones get scattered across various landscapes. And what's nice about bones, right, is we know that they're diagnostic to species, otherwise paleontologists wouldn't have a job, right? But the real questions are, do the bones that are out there on the landscape, do they last a long time? And how representative of the communities are they? And as we start to quantify this is really fundamental to understanding the kinds of ecological data that are available to us. So I'm going to do a lot of this, or I do a lot of this work in what's called a live dead framework. And what that does is it compares the ecological measures of a living population with that community's skeletal remains. And those comparisons are done to assess how well or how poorly skeletal remains mirror the ecological structure of those living communities, right? So we want to test what's the ecological fidelity, how faithful do the bones actually record those source populations. Importantly, we also want to know what kind of biases can we expect. Are certain body-sized animals more likely to show up in the bone record? For example, are larger animals more likely to be sampled in the bone record? Are certain habitats more likely to capture certain kinds of ecological data? What about age classes? We know that young animals, their bones are full of organic material. They're incredibly yummy to various predators. Do they get systematically underrepresented in the bone record? So we do all this, right, to test how well bone accumulations and the quality and the quantity of historical data that's available to us. So the first place I'll actually take you to before we head all the way up to Alaska is Yellowstone National Park. And I did a bunch of work there a number of years ago, and Yellowstone was chosen, or I chose Yellowstone because it has a large variety of fairly undisturbed habitats with significant large mammal populations. And what's neat about Yellowstone, of course, is there have been some biomonitoring efforts that have extended for decades and even over 100 years for some species. Now, one of the challenges for some of those deeply historical data is those are, if you look in texts and reports, it says things like pronghorn as far as the eye can see, right? And it's hard to really put a number on what that means, but at least you can get a perspective about how populations have changed through time. In addition, Yellowstone has experienced a number of perturbations to their ecosystem with which we can test to see if the bones basically pick up those signals. So for example, there was a series of wildfires that ripped through Yellowstone in 1988. In 1995, wolves were reintroduced to the ecosystem, which caused a whole series of ecological shifts, purportedly. And mountain goats actually invaded Yellowstone in the 1990s. So we have an invasive species to basically test what does that look like, or how does that appear in the bone record. Okay. So how do we do this? So the first thing we have to do when we go out there and wander across the landscape is start to get an idea of how bones weather and how long bones can last out on that landscape. And just to walk you through these different stages of bone weathering, and this is sort of based off of the work by Kay Berensmeyer, who's at the Smithsonian, there are essentially 6 stages of bone weathering. Stage 0 is when bones are fresh and greasy and still a little smelly, and they have a few bugs on them. But as the bones start to dry out and they start to crack, we call that stage 1. Eventually, the external surfaces of the cortical bones start to exfoliate away like the layers of an onion. We call that stage 2. And as that exfoliation continues, you get a real fibrous texture on the top of the bone, and that's referred to as stage 3. As the bone continues to weather, you get these large cracks developing, that's stage 4, and eventually that bone will essentially be falling apart and very chalky and feeling. You lift up the bone and it leaves some of itself down below, and we call that stage 5. So one of the early things we need to do, though, is basically calibrate weathering stages to postmortem duration. How long is this record? And the one way we can accommodate this is we can take advantage of the reintroduction of wolves that happened in the 1990s. So wolves were extirpated from Yellowstone in the 1920s, and they were by the federal government. And they were then reintroduced in 1995 as a way to sort of return Yellowstone to its sort of more natural state, quote unquote. And when they did this, they kept track of as many kills as they possibly could. They were trying to really understand what is the impact of wolves on the ecosystem. They wanted to know how the wolves were doing. And each time they visited one of these kills, they would take a GPS coordinate, they'd take a bunch of information on the killed animal, and they would collect one of the metatarsals, one of the major weight-bearing hind limb elements of that carcass. So what I can then do is return to that site, to that same GPS coordinate, find the other metatarsal, measure it, and know that the animal I'm standing over was an elk that was killed, October 3rd, 1998, or August 6, 2007. Right? And from that, I can look at all the bones and see what weathering stages they're in to assess how long each weathering stage takes and how long these stages, overall, how long bones last on the landscape. So if you have decay time along the x-axis, along the horizontal axis, and weathering stage from fresh down at the bottom to heavily weathered up on top at weathering stage 5, what do you see? And so these are the mean weathering stages for each of these carcasses in red. Each carcass is a dot. And maybe unsurprisingly, but quite handily, what you see is as these carcasses continue to lie in the landscape, they get more and more weathered. Right? And a couple things to note is that there's no highly weathered bones. There's no bones in weathering stage 5 after even a little over a decade. Right? And so I needed to start radiocarbon some of these bones to get a fuller picture of how long bones last. And it turns out that bones are lasting for multiple centuries on the landscape. So here you have bones in weathering stages 4 and 5 that are around 200 years old. Well, this was pretty wild. And the take home really is that bones survive up to centuries in temperate settings. So you really do have multiple generations available for study, right? So we've sort of checked off that first box. We have the time. Now we have to assess how well or what the quality is of those data. So the way I assessed that was I ran 40 sample plots in 4 habitats. So 10 each along grasslands, along river margins, forest habitats, and around lake margins. And what I was really doing was basically what I would do is I would mark a midline with a set of flags, and then I would bring out volunteers, mostly undergraduates, and they would walk back and forth and back and forth. You know, they started the midline, walk out 50 meters, walk over a few meters, and then walk back to the midline, and then repeat that over and over and over and over again. So we're really trying to have eyes on the ground for over a kilometer for each of these surveys. So we really were looking at the ground, trying to get a full census of all the bones we found in these sort of 1 kilometer by 100 meters rectangles. And each of these surveys was kept over a kilometer apart. So we would limit the opportunity of bones of one individual being found in multiple surveys. Okay. So once we then sort of took data on all these bones, we could convert the bone sample into the minimum number of individuals. And that's based on species and weathering stage and age. So if I had a fresh elk femur, a fresh left elk femur, and a fresh right elk femur, I would consider those from one individual on the survey. But if I had a very weathered left elk femur and a very fresh right elk femur, I would consider those 2 individuals. There'd be some offset there. So again, we convert this huge bone accumulation sample into the minimum number of individuals, which we can then directly compare to the surveys of the living communities. So if you walked basically 40 kilometers across Yellowstone, how many bones do you think are out there? And again, I wish I could poll you and sort of pull numbers out of your respective living rooms. But I just want you to sit with this question and really give it a thought. I mean, when you walk out in the forests out in Ohio, if you've been to Yellowstone, think about how many bones you think you might find if you really just wandered around. Is it 100? Is it 50? Is it 1,000? So my data set had around 18,000 bones from around 1,000 individuals of more than 40 species, right? And again, that's just from walking across the landscape. And if you start to take a look and think about which species I actually found, all of the native ungulates were recovered in the bones. So I found bones from all of the native ungulates. I found bones from over half of the carnivores. And I'm actually fairly proud of that number. I wish it was higher. But what's interesting about this number is that I'm actually in competition with Yellowstone rangers for these data, because when they find a grizzly bear, when they find a wolf, a coyote, a bobcat, they actually remove that carcass from the landscape to limit the opportunities for poachers to come through, or limit the opportunity for tourists even just to take something that they find is really cool, even though that's illegal. So even though I'm competing with the rangers for my data, there's still a lot of carnivores out there. Lots and lots of birds. I know I'm not going to talk about those at all, and I feel bad about that. But in all honesty, I have yet to key out all those birds. So that's something that's still on my radar. Lots and lots of small mammals, pocket gophers, woodchucks. I could talk about all the small mammals for ages, but I won't today. But the other one I'll highlight is horses, and then I'll come back to horses. But that's a really interesting species to find in Yellowstone. But the real take home here is there's a high body size and species diversity. So not only are they lasting a long time, but they're coming from just about they are coming from every group of vertebrates, of at least mammals and birds on the landscape. So high, and they ranging from shrews, right, the tiniest of the mammals out there, to bison and moose. So high body size diversity, high species diversity. Now, what's the real quality of the data beyond this sort of presence absence? And for that, I'm going to zero in on the ungulates and compare basically the structure of ungulates, of hoofed animals found in the living community relative to the bones I find. And the assumption, the expectation is that the bones should mirror, or at least we hope they do, the living community structure. So the proportional abundances of the living, in this case, I show, almost 60% of all of the ungulates are elk, around 20% are bison, 10% are deer, and on and on and on and on, right? And basically we would expect that the bones, if the record is useful in some sense, the bones should line right up against those white lines. And I'll show you the bones in red. And again, ideally, they would line right up against those white bars. And they essentially do. Which is really nice to see. So by and large, the overall structure of the death assemblage of the bone accumulations mirrors the living populations really nicely. Beyond that, though, if you really start to zero in on things, there are 4 species where the relative abundance of bones of the bones is different from that of the living population. So, for example, I find way too many elk bones relative to the living population. I find way too few bison relative to the living population. I didn't find any mountain goats, even though they live there. And I found a huge number of horses, even though there aren't any horses there. So what's going on there? And what's interesting is these are the 4 species that have changed the most over the last decades to over a century. And if you start to zero in on these, for the native ungulates, for the elk and bison, these are the only 2 species that have changed more, that their current populations are more than 1 standard deviation away from their 20-year population means, meaning they've really changed relative to their long-term averages, right? And what's interesting, and how this manifests is that elk, for example, I mentioned that wolves were reintroduced in 1995, and coincident with that reintroduction, the elk populations crashed. They really, really went down. And so what you're seeing is that the bones of the elk bones are recording this really high, as a historical resource, they're recording that past high population of elk relative to a much lower population today. Bison are doing the opposite. So it turns out that there's way more bison today than there had been in the past, because there's a big shift in how bison were managed. For a long, long time, bison were capped at a certain number, a certain imposed carrying capacity. And when bison populations started to climb above that number, they would just cull them all. They would just kill them. They relaxed that. Bison populations increased nearly exponentially. And what you see then is the bone record is capturing this historical, really depauperate bison population relative to today's very, very high numbers. And then things continue to be interesting, where again, I mentioned that mountain goats are an invasive species. If you look in Yellowstone, there's no record, there's no archaeological, there's no paleontological record of mountain goats ever being in Yellowstone. And yet they recently moved in. It moved in because mountain goats were introduced into the Absaroka Range, which is just north of Yellowstone, for sport hunting, and they basically walked into the park. And what you're seeing here is highlighting this lag between the time it takes for a new animal to show up in an ecosystem and for the bones start to actually accumulate enough to actually be found in the bone record. And then there's horses. And again, I don't know how many of you have been to Yellowstone, but if you go out onto these ecosystems and look around for various animals, you really shouldn't find any horses, right? There are no wild populations of horses out there. So what's going on there? And what's interesting about that is that sort of a brief history of Yellowstone. So Yellowstone became a national park in 1872 by grant. Very, very quickly, Yellowstone was completely ransacked, or at least there was an attempted ransacking of the park, by a lot of people looking for good hunting grounds and a variety of other resources. And so when you are in the 1800s and you need to protect some land, you send in the War Department. And in fact, Yellowstone was overseen by the War Department in 1886. And of course, if you're going to send in the War Department in the late 1800s, that comes with the cavalry, right? And so from the late 1800s until cars were first allowed into Yellowstone in 1915, horses were the only major mode of transportation across most of Yellowstone. So this is a potential hypothetical source of all these horse bones, right? So are these horse bones then a record of a local extinction? A time when horses were all over Yellowstone, and then starting in 1915, those populations were basically entirely removed. And does the bone record reflect this shift in population? So if we start to radiocarbon date various horses that we find out there, we find that they really are an historical resource. So all these three horse bones that I've highlighted here are all from the cavalry. They're all cavalry horses lying out there, just sitting on the landscape. Again, this historical resource, and in this case, showing a local extinction. Okay. So if we start pushing, if we keep pushing, then this is sort of this live dead comparison. We would also think that you might be able to see these shifts within the bones themselves, right? So just, here we did live dead comparisons. What about if you just look within the bones themselves? And what I mean by that is if you take those horses, and if you had at one point lots of horses, and then in the next time point, 0 horses, you would expect that you would basically only find highly weathered bones, right? You shouldn't find any more recent bones, right? This is a simple test that we could do to see if my ideas are working out. And in fact, there's 3 species that have experienced some sort of perturbation over time. Horse is the most obvious and sort of extreme one, but moose and moose and pronghorn also experience population changes, although not as extreme as elk and bison. And so I mentioned in 1988, there was those wildfires that ran through the northern Yellowstone, and that literally decimated the moose population. And so that would be a species you would expect maybe be slightly over enriched in more historical bones. Similarly, around the same time, a few years after those wildfires, pronghorn populations also diminished, embarrassingly, because they all got pink eye, which can be a fairly disastrous disease in ungulates. So again, you might predict that given that historically pronghorn populations were much larger than they are now, you might expect most of their bones to be more weathered. And if you start to look at those bone distributions, and here is the weathering stage again, fresh on the left to highly weathered on the right, horse bones really are only found in deeper weathering stages, and moose and pronghorn are dominated by this weathering stage 3, whereas I won't show it here, but elk and bison are dominated by weathering stage 2. So even looking within the bones themselves, we reveal population changes, right? So not only is this useful for understanding modern systems, but also suggests that there's some utility for looking at fossil situations too, where you can actually look at a fossil deposit and think about how these populations have changed through time in that sense as well. Okay, so what did we learn before we get to the Arctic Refuge? One, we already knew that bones are diagnostic to species, but we were able to finally show that they do last a long time. Multiple generations are available for study, and that they're representative of the communities from which they're drawn. Right? And so Yellowstone bone accumulations faithfully record their source populations, whether that's live dead comparisons or dead comparisons, and they reveal populations in flux that includes invasive species and even local extinctions. So we really can go in the field today, right, and collect this historical ecological data, right, which is pretty exciting. So now that we sort of have explored this system and sort of calibrated it to some extent, let's start to apply it. And the place I'm going to take you is the Arctic National Wildlife Refuge, right? This region is up in the northeast corner of Alaska, right on the Canadian border. It was first protected in 1960. And then the protection sort of went through a second generation in 1980 with the passage of the ANILCA Act, the Alaska National Interest Lands Conservation Act. And as part of that, that expansion of the protected region of the Arctic Refuge and a variety of other sort of details, the 1002 area, the so-called 1002 area, was established on the coastal plain of the Arctic Refuge, and that's highlighted here in this green polygon. Okay, and in this region, drilling was not directly permitted, but it was allowed to be explored and considered. And if you're familiar with Alaskan geography and energy, sort of natural energy interests, you may know that Prudhoe Bay and this entire region to the east of the Arctic Refuge is where Alaska's oil fields are. And so the Arctic Refuge really is an expansion of those same deposits that have been harvested by Alaska for many, many decades now. But of course, the Arctic Refuge represents a lot of things, right? And so if you go out to the refuge, you might see polar bears. This is what these prints are. And if you're really out there alone, hopefully the prints are all you see. It's an amazing stopover site for a variety of migratory birds. Again, I'm sorry, I'm not going to go into details there. And lots and lots of marine mammal wildlife. It's also home to a tremendous number of caribou. Okay, and that's where we're really going to focus for the rest of the talk. And the really interesting part about the Arctic Refuge, and particularly the coastal plain where the 1002 area is it's the calving grounds for one of the largest caribou herds on the planet called the Porcupine caribou herd. And not only is that interesting biologically, but it also has a lot of significant cultural value for the Gwich'in and a number of other groups of Native Alaskans and First Nations Canadians, right, who rely on this herd and other herds for a variety of cultural and nutritional sustenance. So what's interesting about this region, so again, here is that 1002 area that used to be highlighted in green and now is dashed for you. My mouse is, there it is. This large gray polygon is basically everywhere that the Porcupine caribou herd, which is around 200,000 animals currently, has calved in the last basically 3 decades. And the very dark polygons are the regions that are considered the concentrated or high use calving grounds, right? And you can see that there's real solid overlap between the concentrated calving grounds and this 1002 area. And I want to give you show you a video of movements of female and male porcupine caribou throughout the course of a year. And what you're going to see, and I just want to sort of highlight the really interesting behavior of these animals that are, this herd actually makes the longest migration one of, if not the longest, it depends on the year, migrations of any terrestrial mammal. And what you'll see, pay attention to all the red animals, right? The red ones are females, the blue ones are males. And what you'll notice is this herd has a tremendous range, but when spring comes, they all swack right up to the Arctic Refuge and to northern Canada, and then they quickly disperse, right? So they don't use the coastal plain region throughout the year. But when it is time to drop their babies in the early spring, basically all the females of this massive herd, which often will spend a lot of time all throughout Arctic Alaska and Canada, all concentrate in that region for just a couple weeks out of the year to drop their calves. So, but understanding how calving grounds shift through time is really logistically challenging. And over the last around 40 years of study, they've shown a real complex set and highly variable calving patterns. Sometimes they're calving in the coastal plain of Alaska, sometimes they're calving in Canada. And it's been really challenging to understand this variability and to understand what's the impact of developing that 1002 area. Right? Of course, what's interesting is the Tax Cuts and Jobs Act of a few years ago opened up this area for oil exploration. And in fact, the lease sales for the Arctic Refuge were just recently sold earlier this year. But the real question is, can we use skeletal records basically to extend our observational window of calving activity and basically give us some context for what we know about modern systems based on the living caribou? And why this might be possible is that female caribou have antlers. You probably know that to some degree. But what's interesting is that you saw the migration of these females in particular. They go in these massive groups. They migrate to the calving grounds, and then the females shed their antlers within days of giving birth. Right? And so potentially you have this ready-made skeletal signature of calving grounds. And data that I won't show you from working Yellowstone basically showed that where male elk hang out in late winter, right around the time that they're losing their antlers. The antlers basically give you a phenomenal record of how elk actually use that landscape. So the geographic location of elk accumulation, of antler accumulations tells you a lot about landscape use. So can we use that principle for thinking about caribou calving? The first thing you have to do is be able to identify male from female antlers. And if you have complete ones, that's really simple, but mostly what we have out there in the landscape are fragments or incomplete portions of antlers. And so what you can do though is basically measure the area of that ellipse. And females are generally smaller than males, although there is some overlap between adult females and young males, right? But for every antler, you can get a probabilistic estimation of whether it is male or female, so it's useful. So again, huge number of caribou calving on the Arctic Refuge. And the things we want to know are, one, do caribou leave behind that skeletal signature? Do you find lots and lots of shed female antlers? We want to know how long do they last on the tundra, and then we want to be able to test for drivers of changes in calving geography. And why we're looking at large-scale climatic drivers is that climate temperatures can change, and weather patterns can change dramatically across this huge region. But climate is probably a more useful proxy. And the ones we're going to look at is called the Arctic Oscillation. And this is a differential in atmospheric pressure between the high latitudes and the low latitudes, such that when you have, there's a shift of basically when there's low pressure in high latitudes and high pressure in mid latitudes, you get this concentration of cold air up in the Arctic systems. But when you get an inversion of that, when you get high pressures up in the Arctic settings and low pressure down in the temperate latitudes, you get that ring breaks up and you get incursions of the super hyper cold air. And that's called the polar vortex, right? And to give you an illustration of that, that polar vortex can change Niagara Falls into some pretty serious ice climbing opportunities, right? So these are pretty big systems. And the positive Arctic oscillation is when the polar vortex is contained up at the Arctic, and the negative setting is when it freezes Niagara. And we know that caribou biology changes a lot as a function of these large hemispheric scale climate modes. And so, for example, this is some data showing that there is a relationship between the Arctic oscillation on the y-axis and caribou population size itself, right? And from this, we also understand that the growth rate is actually negatively correlated with the Arctic oscillation. So it is changing populations quite dramatically and quite directly. And how the Arctic oscillation may influence the calving geography is here's the theoretical underpinnings. And the idea is, again, these animals, porcupine caribou, are moving up into Canada and then over into Alaska, right? And when there's a larger snowpack and a later melt, they calve in Canada. And when there's ability to move across to the west, they do so, right? When there's less snowpack or an earlier melt. And overall, there's indication that the 1002 area has higher calf survival. So overall, it looks like caribou really are pushing to the west as long as they can. We know that for this region, higher snowfall occurs when the Arctic oscillation is in the positive phase, when those polar vortexes contained up in Alaska. So the prediction is that when you have positive Arctic oscillations, you should be calving basically more in Canada, more eastward calving, right? And potentially antlers can provide this information. Okay. So do you find a lot of antlers out there? That's the first question. So I'll take you to the heart of the calving grounds in this place called the Jago River in the heart of the 1002 area. And just to give you some travel photos, we get out there in these small planes. We fly across these Arctic scenes. The camping ain't half bad. A lot of caribou that you see out there. But mostly what you see is pictured here. And this individual, this is the manager of the Arctic Refuge. He's absolutely surrounded by the things that we deal with day in and day out, which are mosquitoes. And if you can read this, this says 60 seconds of opening and closing on the Jago River. These are all mosquitoes, and here's one coming to meet his friends, right? So it's just, it's fairly out of control. This is not for the faint of heart. It's pretty gross. But the point being There's four generalized habitats in the Arctic Refuge. There's tussock hummocky tundra. And if you've ever been out there, or if you haven't, there's these large tussocks of grass. And they're sort of wobbly. It's kind of like trying to walk on a whole bunch of camels that are all strapped together. It's really challenging to move around in. And that's about half of the coastal plain. Moist wet sedge is another 40%. These are smaller and fewer tussocks. And then there's barren gravel riparian shrub, which is fairly rare, very flat, more open. And then driest terraces, which are quite rare on the Arctic Refuge coastal plain, very flat, very open, very low vegetation. And so within the context of calving habitats, one of the things that we did early on is to basically compare these different habitats to see what the antlers could tell us. Overall, there's an understanding from aerial surveys that tussock hummocky tundra and moist wet sedge were the dominant calving habitats. And we wanted to see if the bone could provide some novel insight. So very similar to Yellowstone, we walked 1 kilometer and 100 meters wide, again, walking on either side of that midline, 50 meters out. And back to midline, again, 50 meters out on either side and back and forth and back and forth. And here we're just counting up antlers. And eventually we'll convert that number of antlers into antlers per square kilometer. So just to show you, and I know I'll wrap up here in just a few minutes. I know I'm getting close to time, here's just a representation of these 4 different habitats. I'm just going to show you basically a sort of a rectangle and then some dots representing the antlers that I found. And the context here is that antlers were really never previously observed in measurable quantities. And as I was trying to start this project, I like to say that I've been laughed out of most federal and state Alaskan wildlife offices because they had worked there for so long and just never seen antlers out there. So let's start looking at what we found. So you go in the tussock hummocky tundra and you start to understand why this idea didn't really make too much sense. And here's the moist wet sedge, again, some antlers, but not a lot. But then here's barren gravel riparian shrub, and here's the driest terrace, right? And so there are real concentrations of antlers out there, but they're only in certain habitats. And in fact, they're in fairly rare habitats, right? And so, in exciting table form, generally what you see is there's, upwards of 112 or so antlers on these surveys. Most of them are females. And if you start to convert them into antlers per square kilometer, going upwards of 1,000 antlers per square kilometer, right? And these are very, very obviously different in these different habitats. This abundance is pretty striking. And even though the tussock tundra habitats had, one hypothesis would be that maybe we're finding fewer antlers because they're being buried in the vegetation. And although that is true, you get bones being buried in the vegetation, the sheer quantity well over exceeds these sort of buried bones, right? And we're also finding huge amounts of rodents in all these habitats, so we don't think there's a visibility bias. So we really do think that these bones are providing useful and novel data. And the last thing I'll talk about, I won't discuss the third point today, is basically how long these bones have lasted on the landscape. So here's weathering duration from 0 to many, many hundreds of years, which should give you a clue where we're going. And basically what's going on is, we're finding antlers that are over 700 years. In fact, at this point, we're finding antlers that are thousands of years old. Here's, for reference, the Christopher Columbus sailing the Atlantic. So we have a real extensive record of antler distributions out there of calving. And this is where calving surveys begin. So this is our current data on wildlife of caribou, and we're really filling in the details of the historical state. And the last thing, I'll just sort of blow through this a little bit. So kind of ignore this, that's all right. That's just showing that basically you can identify antlers, get an idea, an estimate for how long they've weathered based on or how long they've been sitting there based on their weathering stages. And to show you some highlights of some other ones, right? This antler, this is over 600 years old. And you can see this little bit was hanging out in the tundra, and the rest of this was exposed from digging. Another one of my favorites, here's another one that was just sitting on the tundra, and that's from 2,600 years ago. So again, you're getting this real long tail of historical insight, which is pretty nifty, right? And ultimately, that's sort of the take home, is you're getting a tremendous amount of historical insight. And if you really start to study these landscapes across the Arctic Refuge, just targeting the driest terrace now, where we know we find a lot of antlers. And you start to explore the historical change in geography across time. And basically, once you take the entire data set and you say, where are all the antlers from the 1980s across space? Where are all the antlers from the 1990s? Where are all the antlers from the 70s and the 60s and the 50s and on and on and on? And compare those to these Arctic oscillation values I mentioned before. So if you have the Arctic oscillation on the horizontal axis, and then Canada up to Alaska along the Y, what you find is that the antler data are suggesting that across large decadal timescales, and again, to remind you what's going on, like that point is all the antler data from the 1980s, right, relative to the Arctic oscillation of the 1980s. You show that more positive Arctic oscillation values drive calving to the east. More negative Arctic oscillations drive calving towards Alaska. So, incorporating what we already know about the Arctic oscillation, and here's the Arctic oscillation over the last several decades. But if you pull back a little bit, we know that the Arctic oscillation was actually fairly a bit more negative for the previous 100 years starting in 1850, suggesting that 1002 area in Alaska may have had a much greater historical importance even than it does today. So we're really trying to incorporate this information in. So what's the point? What are the critical calving habitats of the Arctic region? Well, they're these rare habitats. They happen to be flowing right along these rivers. How long is the available record? Well, it turns out it's centuries to even millennia. And it turns out that these large hemispheric modes, the Arctic oscillation in particular, seems to be driving caribou landscape use in a pretty serious way. So the final point I'll leave you with is that we know that climate and biology dictates where animals can live, but we also know that politics and borders influence where they actually do live. And often we only have several decades of data on ecosystems globally. We know that baselines have already significantly shifted. And fortunately, we now understand that bones can fill in a lot of this historical information that we've been missing for a long time. So with that, I'll just thank folks in Yellowstone and my partners up in the Arctic Refuge. And of course, for you for listening and the invitation. And I'll stop there and take some questions.
Thank you so much, Dr. Miller. That's fascinating to hear about the way you're able to get so much information from these bones. I'm curious, you mentioned about the Arctic Oscillation, how it seems to have been more negative in the past. Is that directly attributable to human activity, or is that somewhat of an anomaly?
No, so the Arctic Oscillation is really interesting. I'm trying to find me and anybody else. I feel like, oh, stop sharing, that's what I should do. So the Arctic Oscillation, unlike things like El Nino and La Nina, which is highly cyclic, the Arctic Oscillation itself is just not as cyclic. It's fascinatingly not cyclic. And we know less about that particular mode than a variety of these other modes. But no, that's unlikely to be human related. That's just sort of the vagaries of the Arctic Oscillation. Additionally, what's quite interesting is that as you go back in historically, back towards the early 1900s and more interestingly to the late 1800s, that's a time called the Little Ice Age. And up in this region, it was also much, much drier than it is today. And so not only is the Arctic Oscillation probably important for these ungulate populations, caribou in particular, but local precipitation will also change that. If it really is about how far west you can go, if you dry that region up, if you don't have a lot of snow to fall, that also may be driving caribou towards the west into Alaska. So again, potentially multiple hypotheses for climatic drivers of caribou calving geography.
And Dr. Miller, I had a good friend who actually studied ice cores to examine past climatological data. Is that something we can actually measure from some of these bones, or is that more of a trying to guesstimate the age and the population and then draw conclusions towards what the climate may be at that time?
So I mean, the short answer should be probably no, but the more creative maybe yes. And so the reason I might say that is antlers are really interesting. Right, here's one. Because you know, they're grown in such a brief amount of time, just a couple months, right? Which is one of the interesting things about antlers. And caribou, male caribou have the largest, per body size, the largest antler of any of the deer. And again, they're grown in just a few months. What's neat about that is we know exactly when they start and when they're dropped. For the females, they start growing them in basically, you know, June, depending on the latitude you're at, and they're fully ossified just a few months later, which means every time you find a shed antler, or anytime you find a fully complete antler, you know the season in which it was grown. Now, what's cool about that is if you have a time series of antlers on your table, for example, here's a time series of antlers on my table. If you know the dates in which each of these are grown, and you look at the oxygen isotopes of those antlers, you might actually be able to see some meaningful shifts. So again, if you can keep the herd itself or the geography constrained, and since you know the season is entirely locked in, those changes in oxygen isotope values may actually be an interesting way to explore changes in local climate. So it's an interesting idea.
That is quite amazing that you can tell so much information from a simple bone, something that most of us overlook, I think, on a daily basis.
I'm here to help.
And Jim Michael had a great question. He asked, do you age the antlers completely in the field? Or do you retrieve them, bring them back to a lab, process them, and do that radiocarbon dating?
That's both. So every antler that I come across is collected completely. And so the University of Cincinnati Collections has a really neat opportunity to think about this sort of at the assemblage scale. So lots of them get radiocarbon dated. So, you know, let's see. So here's one, and this, you know, this has been cut out and high grade. The bone has been high graded to take the very middle of the bone that's in great shape, and that gets dated directly. So the collagen gets extracted and we date that collagen. But a lot of what I'm also but each date costs about, you know, depending on how you do it and what the things, that's about $350 on a good day. And so of the thousands of antlers that I have looked at, we can only date a small fraction. And that's why I'm developing the scales of, and that was the thing I blew right past, so I apologize for that, looking at the different ways the bones weather, the different states of lichens. There's beautiful lichen development that occurs on these antlers. Understanding all those features can give us an idea of, give us a temporal estimate. And we can estimate, currently, those data that I showed you, those are all estimated sort of plus or minus a decade or two in terms of when they were grown, if you're doing it by weathering features. Ideally, we could date everything. So if anyone knows of a billionaire that's looking forward to sending their money to poor scientists, that's a great project. But I'm also really excited about developing these systems that you don't have to directly date everything, because that's also useful for the fossil record. Great question.
I'll reach out to all the billionaires I know, and I'll send them your way, Dr. Miller.
Thank you. That's good.
One final question for you. You talked about the different weathering stages of these bones. I'm curious if you know the science behind or have witnessed yourself, do different bones from different species weather more rapidly? Maybe that's an amount of calcium in the bone or some type of factor there.
Yeah, no, it's a great question. So what we think is that body size plays the major role. So if you have, so caribou are fairly small-bodied animals, but if you, and so they tend to weather at different rates than things like bison and horses, which just have beefier bones. And horses are a great example because their bones are incredibly dense, incredibly, you know, overbuilt. So bison bones and horse bones may also weather slightly differently. Another driver is age. And so if you have an animal that's still rapidly growing, becoming an adult, their bones weather faster because they have so much more organics in them. So all those things come into play. The nice thing about antlers is that they're all pretty much the same, which is convenient for this kind of study, right? So you don't have those vagaries. But that is really important for understanding bone weathering more broadly. Absolutely, absolutely.
Dr. Miller, thank you so much again for speaking with us tonight. It's been fascinating, even though we don't focus on birds in this presentation. It's still fascinating to see all the science and all the work going on behind the scenes here. So if you would
also highlight that birds do also consume bone, as I'm sure your audience is aware of, especially when they're retrieving calcium when they're laying eggs or prior to. And you can there are specific kinds of bone damage, particularly in the woven bone, the sort of spongier bone of long bones, where you can, the bird will be pecking right into that bone and reclaiming them. And I noticed there's a question about rodents. And so that was one of the concerns, that rodents would be gnawing all the antlers away. But it turns out there are very few rodent gnaw marks on these antlers. But what's really interesting, I'm not sure if you can see this, but the end of this bone has a wavy texture to it. And that's not rodents, and that's not carnivores, that's actually caribou. So the major consumer of bone of these antlers is in fact the caribou themselves. And so one of the neat things that's coming out of this research is a greater appreciation for how much caribou utilize their own antlers during their life cycles. And so when they're dropping their antlers, right after they've dropped their antlers, which they have also dropped their babies, they're suddenly in a huge amount of lactation demand, and they're starting to regrow their antlers again. And they're in huge need of calcium and phosphorus. And what's neat about caribou is they've brought the nice source along with them. So they're actively using and harvesting that resource across the landscape. Anyway, thank you all.
That's quite amazing. And they're traditionally herbivores, aren't they?
Well, and they still are, but but ungulates. This is a thing that ungulates do. We know that deer. This has been studied a fair bit in deer in general. And when deer are nutrient stressed, they will consume bone. And often, if they don't have salt licks around and these sorts of things, they will turn to other resources, particularly during periods of hardship. And so the caribou are doing that also. And here we're showing that they're doing that in a big, big way. And it's not to say that other species don't, but it's not very well studied. But up in the Arctic Refuge, where you have, again, one of the longest terrestrial migrations that we know to ever exist, it comes with all these other pressures. And one of the releases of these pressures is to consume their antlers.
Wow, that is fascinating. Yeah, if you wouldn't mind in the future, please keep us abreast of all your research or any publications. We would love to post that on our website and tell our members about that. And Dr. Miller, again, I can't thank you enough. It's been an absolutely fascinating talk. And I know for me, as a self-proclaimed bird nerd, I definitely learned a lot.
Very good. Well, thanks for having me. Good to not see you all. Maybe we'll see you another time.
I appreciate it, Dr. Miller. Thank you so much. And thanks everyone for attending, and have a great night and be safe out there.